Hello everyone. In this video, we are going to discuss some more realistic models of simple harmonic motion. Previously, we considered some idealized models. Now, let us have a look at some realistic models. Okay, so we'll start with, again, a spring mass system. Now, previously, we considered that the spring was massless, right? Now, in this example, we are going to attach some mass to the spring. That is, the spring will have a finite mass m. We are going to call this spring a physical spring. Now, what should be the equation of motion of this physical spring? We can find that out by first finding out the energy of the physical spring. Let us first find out the kinetic energy of the spring. Now here, for this spring, the velocity at this fixed end is always 0, right? And at the free end, at distance x, the velocity is v, or we can call it x dot, right? So what should be the velocity of a small segment in between? Well, let us take a small segment here at some distance s, okay? So the velocity here should be equal to the velocity at distance x, which is x dot, divided by that distance x times this distance s. So this should be the velocity of this small segment here, okay? And what should be the mass of this small segment? Well, if the total mass of this spring is capital M and the distance is x, so the mass of unit length is m over x, and if this has a length of ds, then this is the length or the mass of this small segment, okay? We can call that dm. Okay, so now let's find out the kinetic energy for that small segment of the spring. So the small kinetic energy of that small segment should be equal to half times mass times its velocity squared. So the expression for the velocity was given by this, and the mass of that small element was given by this. So this is the infinitesimal kinetic energy of that infinitesimal element, okay? Now, in order to find out the total kinetic energy, we have to integrate this thing throughout the length of the spring. So the limit would be from 0 to x, okay? So if we integrate this out, we get the total energy of the spring. So here is the total kinetic energy of the spring. But remember, we have a mass attached to the spring. So the total kinetic energy of this system, of this physical spring, would be the kinetic energy of the spring added with the kinetic energy of the mass. Now, if the mass attached to the spring has mass equal to small m, then its kinetic energy would be a half m x dot squared, okay? And if we add the kinetic energy of the spring with it, we get this expression. Now, if you have a closer look at this kinetic energy term, you'll see that it is a typical kinetic energy term, right? Half some mass times x dot squared. But here, due to the mass of the spring, we have this extra term, okay? So this is the main difference in case of the total kinetic energy. What about the potential energy? Well, the potential energy is actually the same. It is half k x squared, which again, you can say that it follows from the Hooke's law, okay? Now, the total energy will be the sum of this kinetic energy plus this potential energy. So we have this as the total energy of this physical spring. Now, as you have the expression for the total energy of this physical spring, can you find out the equation of motion for this physical spring? Well, actually you can. what you have to do is you can apply the energy conservation formula, right? That is dE dt will be equal to 0. So if you differentiate this thing with respect to time and put that equal to 0, you can find out the expression for the equation of motion of this physical spring. And from that expression, you can actually find out the angular frequency of this simple harmonic motion, okay? Now, actually, you don't really need to find out the equation of motion in order to find out the angular frequency, okay? Because you can always compare this expression with the ideal expression of a massless spring mass system, okay? Which was this one, right? Total energy half mx dot squared plus half kx squared. So if you compare these two equations, you see the mass is replaced by this quantity, right? And previously we saw for this expression the angular frequency was square root of k over m. So now logically the angular frequency here should be k over this mass term, which is small m plus capital M over 3, okay? I would suggest you to find this expression out from this condition, okay? Okay, so now let us have a look at another example of oscillating systems. Let's consider elastic bodies. Now, what is an elastic body? Well, an elastic body is if you apply some force on that body, it deforms, okay? But if you remove that force, it goes back to its initial shape or size, okay? So rigid bodies are actually elastic, but we normally don't notice it always, right? For example, let's say we have a rod or a wire hang like this from a rigid support. So if it carries some weight at the bottom, actually it will stretch, right? Now if we just stretch this a little and release it, it will do some kind of oscillation, right? And this is due to the elastic property of this wire, okay? Now, what is the thing that characterizes an elastic object? Well, you can say that an elastic object obeys the Hooke's law. That is, the force is proportional to the deformation, okay? But here you can say another thing, that is, the extension under the force is actually proportional to the original length. These two statements are equivalent. So what does it mean? Well, as you can see, here we have an elastic object here. So if this length is L0, then if we divide it into 3 halves, it should be L0 over 3, twice L0 over 3, and this should be L0, okay? Now, if we pull it by applying this force, delta F, well, it should increase in size. So where should this point go? Well, according to this statement, it is proportional to this initial length, L0 over 3. So it should be delta L0 over 3, okay? And what this should be? Well, it should be proportional to initial length here, which is twice L0 over 3. So here the extension also will be twice delta L0 over 3. And here the initial length was L0, so the extension should be delta L0. But instead of these deformations, you can see that this ratio, which is delta L0 divided by L0, is applicable to all 3 cases, right? So you see, if you divide this deformation by this initial length, this deformation by this initial length, and this deformation by this initial length, you always get this quantity, delta L0 over L0. This is what we call the strain. Now, this deformation that we talked about due to this force delta F, actually this kind of deformation can also happen in case of an increased delta F. But for that, we have to increase the area as well. So that means the ratio between delta F and A is actually the reason for this similar kind of deformation, what we called strain. This quantity, delta F over A, we call this the stress. And this is actually another form of Hooke's law, which says that stress is proportional to strain. But they are proportional up to certain limit, where the strain is very, very small. We call that limit the elastic limit of that elastic object. So in the elastic limit, stress is proportional to strain. So this is our stress and this is our strain. So we can write down stress to be equal to some constant of proportionality times strain. Okay? We call this constant of proportionality Young's modulus. This Young's modulus is the property of the material of that object. Now, from this expression, actually you can find out the force acting on that elastic object to produce a deformation equal to delta L0. If you know Young's modulus, the initial length of this object and the cross-sectional area. Okay? Now, according to Newton's third law, if we apply a force F in order to stretch this elastic object, this object will also exert a reaction force which will be equal to that force but in the opposite direction, right? So we can write that down to be equal to minus of the force found from this equation, that is this quantity. And as this y, the Young's modulus, A and L0 is constant, we can write this out as K, right? So this will be the restoring force in this elastic object. Now, this restoring force should remind you that this is the similar kind of restoring force in the mass spring system, right? So this object should also go through a simple harmonic oscillation. Now let's find out the equation of motion for this kind of simple harmonic oscillation. So for example, let's imagine this system where from a fixed support we hang this wire, an elastic wire, and attach a mass here at this end. So if the initial length is L0 and after attaching this mass, if it increased the amount delta L, we can write down the restoring force here to be equal to minus K dot this extension delta L, which from Newton's second law we can write down as MA, where A will be equal to second derivative of this extension delta L with respect to time, that is the acceleration. Okay, so now let's rearrange this equation here. Okay, so you can see we get that similar K over M term, which we can define again as omega squared. So this may look similar to you. In case of a mass spring system, we got X here. Now we have delta L instead of that X, right? So the solution of this equation of motion should be a similar quantity like this. That means this delta L, okay, will vary with time, and as this is a sinusoidal or cosinusoidal function, it means that it will vary periodically, right? It will do a simple harmonic oscillation. And what's the frequency of this oscillation? Well, we can find that out from this angular frequency omega, okay? Because frequency and angular frequency are related with this equation. And if we put the expression of omega here, we get the expression for the frequency of this oscillation. Here is a numerical example of the concept that we studied earlier. Okay, so here you can see we have this object attached to a wire, which is again attached to a wall like this. So here all the quantities are given, like you see the mass of this object, the length of this wire initially, and the diameter of that wire. Okay, now here 24 AWG, well, it means American wire gauge. So it is a convention of defining the diameter of different kind of rods or wire. Okay, so you don't need to worry about this. Now from these given quantities you can find out the restoring force, also the spring constant, right? So you can find them out, and as you can set this restoring force F to be equal to mg, from that you can find out that extension of the length as well. Okay, again you can find out the frequency of the oscillation of this object by using this expression. Okay, so now let us consider another example of simple harmonic motion, that is floating objects. Okay, so for our purpose let us consider a hydrometer. Well, what is a hydrometer? Well, it measures the density of liquids. Okay, remember there is another instrument called the hygrometer, G here. Well, that measures the humidity of the air. Okay, so we are considering hydrometer here. So how does it work? Well, the liquid of which you want to measure the density, you take that in a measuring cylinder. Okay, and then you put this hydrometer on that. Now as the hydrometer goes into the liquid, there will be some buoyant force due to Archimedes' principle, right? Now at the equilibrium position, the weight of this hydrometer should be equal to the buoyant force, right? So then from those equation, actually the force acting on this object due to buoyancy of the water should be equal to the weight of this object. Okay, so from that you can find out the density of the liquid. That's fine. Now where does the simple harmonic oscillation come from? Well, in case of the equilibrium position, if we just push this hydrometer a little in any direction, then you will see there will be an oscillation going on here. Okay, so let us first analyze the force acting on this object, that is the buoyant force. Well, according to Archimedes' principle, the buoyant force is equal to the weight of the volume of liquid displaced by the instrument, right? So first we have to measure the volume of this portion, right? After which it is under the liquid, right? So here this hydrometer has actually three parts. We call this slim portion the stem, this bulk portion the float, and this head a ballast. Okay, so let's say the volume of this portion without the stem is V0. Okay, so the total volume occupied by this instrument under this liquid should be the volume, this one V0 plus this small volume whose height is h. Okay, so as this is cylindrical, its volume should be pi times this height h times the radius of this stem squared. Okay, so if its diameter is d, then its volume can be written as this expression. So this is the total volume occupied by this object under water. Okay, so according to Archimedes principle, what is the buoyant force? Well, the buoyant force is the weight of this amount of water, right? So we have to multiply this volume with rho, that gives us the mass of that liquid times g. So this is the total weight of the liquid which would have occupied this volume. Okay, so this is the buoyant force. Now, in equilibrium position, this buoyant force is equal to the weight of this hydrometer, right? So let's call that mg. Now, typically for a hydrometer, you tend to find out this rho, the density of that liquid, from the other quantities. Okay, for our case, let us find out the expression for this height h. So after rearranging this equation, you should get this expression here. Now this h is the equilibrium height of this hydrometer and this liquid. Okay, now if we push this hydrometer a little in this direction, then this height will increase a little, say delta h. But then the force will not be nullified due to gravity, right? So there will be an extra force. So we can calculate that extra force. What should be the force? Well, due to this height h, force is rho g times this quantity, right? Now if we increase this h by amount delta h, then the force acting, that extra force acting here, should be equal to rho g times pi delta h d by 2 squared. Okay, so that is that extra force. That minus sign indicates that this force will act in the upward direction, which is opposite to the direction where we pushed the object to, like the downward direction here. Now, this equation might look a little complicated to you, but if you see closely, all these things here are constants, right? So you have this force which is equal to minus some constant times that extra displacement. Do you remember this thing? Well, this is just like the Hooke's law or the restoring force, right? F equal minus some constant into displacement. So again, we should have a simple harmonic motion, as you can see from this expression of the force. By applying Newton's second law, we can write down that restoring force to be equal to ma. Here a is the acceleration, which can be written as second derivative of this extra displacement delta h with respect to time. Okay, now rearranging this equation, you should find out omega from that expression, right? For that, you need to compare this expression with this ideal expression. Okay, now we'll consider another example of simple harmonic oscillation, but here the force will be a shear force. Okay, now what is actually a shear force? Well, a shear force is a force where the displacement is parallel to the direction of the force. Say for instance, in this situation, if we apply a force parallel to this plane like this, and if this surface is fixed, then it will deform like this, right? So as you can see, the deformation due to this force will be in this direction, right? Say by an amount x here. So this kind of force, we can call this a shear force. Okay, now again, the shear stress, which is the force F here divided by the area of this surface here, will be proportional to this angle, as you can see. So if you apply a larger amount of force, this angle will increase, right? So the shear stress is actually proportional to this angle, which is actually can be thought of as relative displacement. That is, this displacement x over the length of this object, which is L. Okay, so we can write down the stress, the shear stress here, to be proportional to this alpha, which will give you a constant of proportionality, which we can call the shear modulus of elasticity, or simply shear modulus. For example, steel has a shear modulus equal to this. Now, the shearing force here can create a torsion or twisting force in objects. So for instance, we have an object like this, a thin-walled tube, which is fixed at this end. Now, if we apply a shear force here, this tube will be twisted, right? We can actually measure the shear force in terms of the other quantities. So the angle of deflection here, theta, should be equal to, actually it is the relative displacement I said. So this is the displacement x, and if this length is L, then this is the angle of deflection, which we can also write as r theta divided by L, where r is the radius of this tube and theta is this angle, which we also call the twisting angle. So from the equation of the previous slide, which was this thing, F over A, the stress to be equal to this, we can find out the shear force would be equal to shear modulus times the relative displacement times the area, right? So here you can see the shear modulus times the area times the relative displacement, which we here call the angle of deflection. Now, as there is some kind of twisting going on here, there is actually some kind of torque as well, right? So you can find out that torque here. For that, you have to first find the expression for the torque on this infinitesimal element, and then if you integrate throughout this whole circle, you will get the torque on this object. Here that calculation is done, and I will leave it as a homework to you to do this calculation on your own and understand it yourself. If you have any question, you can ask me in the live class. Now, the torque that you get from this calculation can be written to be equal to I times alpha. That is, the torque is actually equal to I alpha, where I is the moment of inertia and alpha is the angular acceleration. We can write this alpha as theta double dot as well. So we can write down the previous as this expression. We have this minus sign here because of the restoring torque we talk about, okay? So by comparing this expression with this ideal expression, we can find out the angular frequency as well. Now, this expression is analogous to the expression that we saw in case of a mass spring system, where we had x double dot plus omega squared x to be equal to 0. Okay? Here, the angular quantities are considered, so we have this expression. But again, this is a simple harmonic motion equation. So that means if we twist an elastic object like that and leave it, it will do a simple harmonic oscillation. By twisting, we call that a torsion pendulum. Again, I encourage you to do this calculation of torsion pendulum on your own. Now, here is a simple numerical problem which tells you to calculate the frequency of the oscillation which you can easily find out from the expression of angular frequency. Okay, so time for another example. It is for a physical pendulum. A physical pendulum means a pendulum where do not ignore the mass of the thread or wire or whatever we talked about, right? So previously we considered a pendulum where the mass of the wire were ignored, right? Now let's say we have an extended object like this and we have a pivot point here, and if we just turn it like this and leave it, it will do a simple harmonic oscillation, right? So again, I will leave it to you as an example to find out its equation of motion, which again you can see that it should be in terms of the angular quantities because it is the variable here, okay? And it will relate to the moment of inertia as well, okay? So I encourage you to go through these calculations as well. So you see, after doing a little calculation, finding out the moment of inertia of that stick, and then writing the equation motion, you can find out the angular frequency as well, okay? Similarly, I encourage you to do pendulum, the ring pendulum, okay? So if you have a ring of metal like this and you attach to a pivot point like that and move it in this direction a little and then release it, it will again do a simple harmonic oscillation. And in the manner that I described earlier to you, you can find the equation of motion for this one as well. From that, you can approximate the angular frequency of this simple harmonic oscillator. So again, I encourage you to do this problem as an exercise as well.